welcome to our talk on efficient generic microarchitectural hash function recovery. This is a joint work with colleagues from Saarland University as well as from CISPA. And today we're not only going to talk about microarchitecture, but also a little bit about container ships. So start right in with caching. What is caching and how does it look in real life? So imagine you have a factory somewhere and you have consumers that want to buy goods from this factory. So how would you get stuff from the factory to those consumers? Well, the answer is obviously a container ship, as I alluded to before. So basically people order something, you ship it via the container ship. The trouble now starts if people order something again. Well, then you have to drive the container ship back and deliver the goods again. And this is obviously not what you're going to do in practice. In practice, you're going to build some delivery center in between that has storage that stores this stuff. And this is also exactly what we're doing in hardware. So we also install these storage facilities into our processors that are intermediates between the DRAM and the processors, and these are called caches. And a cache in hardware works exactly like the example we talked about before. So the processor orders some data. It first asks the cache, hey, is the data there? The cache says no. Well, then the cache asks the DRAM has the data and delivers it to the cache. Now the data is in the cache and goes back to the processor. And the interesting stuff comes when the processor orders this data for the next time. So then the processor can ask the cache, and the cache can reply, yes, I have this data, and immediately respond to the processor, which is very, very quick, which is nice because we want our processors to go fast. Well, and caches are organized like this, but if we look into the cache, we quickly see that it is not as trivial as this. There's not just one block of storage, it gets a little bit more complicated. And let's jump back to our analogy, where we basically had this container ship. And now imagine you put everything from this ship into one center where you store it. That would be quite messy. So what you do is you basically split it up. You, for example, get a phone delivered, and this phone goes to one warehouse, and you get a t-shirt delivered, and the t-shirt goes to the other warehouse. And exactly the same you are doing in caches. So in a cache, you also have different slices. These are subpartitions of the cache. And these slices are addressed depending on a linear combination, or as we see later, nonlinear combination of the address bits. So if you want a specific address, this address always maps to one or another slice, which distributes the load over the cache. And for example, one address may map to the first slide, where another address may map to another slice. Well, and in the remainder of this presentation, we're basically going to talk about what these slice mapping functions are doing and where we can find them in hardware. Because it turns out these are quite a popular class of function, which we termed microarchitectural hash functions, which are there to distribute load among the hardware. And for example, they appear in cache slices, they also appear in DRAM addressing, they also appear in the cache way predictor, as well as in prefetchers. And what they all have in common is that they're all small functions that do load balancing on the hardware side. And we are going to look at potential applications of this function, especially the cache slice function. So why do we care? Why would we need to know about them? Well, we found, first of all, 3 different very compelling use cases why one should care about such functions. So first, on the attacker side, you need them for sophisticated attacks. If you target a special part of the hardware, you need to know what you're targeting. So if you, for example, mount side channel attacks on the cache, you want to know which slice is the victim accessing so that I can target that. So you would need to know this function. On the other side, you can also use it for optimization. So if I know more about how the cache is structured, well, then I can write algorithms or software that has better cache utilization and basically makes the most of how the cache is structured. And then the last thing you can do, as I said, basically all these functions separate some microarchitecture element. You can basically allocate memory in such a way that you never have an attacker and a victim accessing the same subpart of this microarchitecture element, which is interesting in, for example, the cache, where such a thing can or could prevent cache attacks. So these functions are all very interesting to know, but the problem is they are all intellectual property, and this is basically the same for all of these functions. They are very poorly, if at all, documented, and in the newest processors we could not find any documentation on them. So what we can do is we can reverse engineer these cache slice functions, and this, or other microarchitectural hash functions, and this always works with a similar approach. First, you basically have to measure which address maps to which cache slice or which index in some microarchitectural data structure for the other functions. And then you have to find a minimal or small enough function representation that you can work on that represents these mappings. And we basically did work on both of these sides. First, we built a completely new measurement framework that allows to measure cache slices and other microarchitectural hash functions. And for the cache slices, we had, for example, two cases, but these generalize very well across all microarchitectures. Either you have some performance counter inside that, for example, tells you, well, this access mapped to this cache slice, or what you can also very often use, and which we have a lot of experience with the tons of sidechain research that have been going on in the recent years, is using timing measurements to infer, for example, these cache slices or other indexes into microarchitectural data structures. And so let's jump right into a small example where we basically measure a cache slice function here on the right side, basically that has 3 bits that are all different combinations of the addresses with performance counters. So what we basically found is that you can do a divide and conquer approach where you assume that all bits of the function are independent, all output bits, and you measure each bit individually instead of the entire function like previous approaches. And so by doing this, you reduce the measurement space. And how do you measure? Well, to activate the cache and press data through the cache, you use the CLFlush instruction to activate a specific slice, and then you read out the performance counters. And afterwards, you can basically look at which performance counter has the most activation, and that maps to the cache slice. With timing, it would be a little bit more complicated, but this is also the more general way. You do not always have these. You do not always have these performance counters that allow you to read out the cache slices. So with timing, there's the insight that you can replace the performance counters because the slices have a different latency depending on the core. So for example, you activate a slice with CLFlush and record the timing, and then you hop among the cores, and because all the cores are basically interconnected and have different distances to the cache slice, physical distances, they have a different timing to that cache slice. And then you record the timing, and we see now that we basically arrived at a very close slice now, and this is the lowest timing, and therefore also the closest slice. Well, and then we can basically work with these measurements, right? And it turns out that that's very true. If we have a power of 2 slices, then we have a linear functions, and it's just an XOR of address bits. Why is that the case? Well, this is because if you just take the XOR and you have a power of 2 and the input is randomly distributed, you also get a very nice random distribution or uniform distribution on the output, which is very nice because you want to perform load balancing. But on modern processors, you have non-power of 2 cores and therefore also non-power of 2 slices or performance and efficiency cores. And therefore you get a nonlinear function, which can be an arbitrary Boolean function, for example, like this one here on the right. And I already talked a little bit about it before, but why do we need these nonlinear functions? Well, because load balancing does not work well with only linear functions if you have a non-power of 2 cores or slices or indices in your microarchitecture element. And one of the things is that the core count or the size of your microarchitecture buffer can't double every year. So basically Well, you at some point need to have some trade-off where you don't have a power of two. And on the other side, we have like performance and efficiency cores on newer machines now, and they get different number of cache slices. So for example, the performance cores basically get a bigger part of the cache, and that is useful because they can do more memory accesses than these smaller efficiency cores. And it brings us basically to how do we find these minimal functions, and what is the problem with finding minimal functions if we assume that we can now have basically arbitrary Boolean functions as these cache slices. Well, we know that there's a minimal function representation or something small that is manageable and built in hardware, and we ideally would like to recover something like that or something equivalent to that. Well, for linear functions this is quite easy. For non-linear functions, minimization is provably hard in general. So function minimization is a hard problem, and we have almost no hope to solve it efficiently. The question is there a more efficient approach for what we are doing? So we are not solving this function minimization in general, but for the special class of function that we basically encountered with cache slices and other microarchitectural hash functions. So there is one very, very popular algorithm that instead of trying to minimize something optimally, minimalizes heuristically, and this is the espresso algorithm. And it's the de facto standard for logic minimization, but for our use cases has one very significant drawback, and it's that it works on a DNF representation of a logic formula. And the DNF representation is problematic if we have a lot of XORs, because if you have these XORs, then you have these linear formulas that are a chain of big XORs, and you have to unfold them into DNF. So for example, you see how you unfold the first term here, and if you have more linearity, then the representation gets more inefficient, and gets especially inefficient if these terms are nested. So if you imagine that x1 and x2 would both be another term that contains XORs, then this gets really, really ugly really quick. So it doesn't minimize well because the basic representation is already insanely large. So we basically need to switch to another representation to represent these functions that we encounter in microarchitecture hash functions very efficiently. Well, and this is mainly the XOR, and so we can just encode these formulas as polynomials, and we see that basically we get an exponential blow-up for representing an OR, but our formulas that we found didn't contain very many OR operations, so we do not care about this. And so we see basically that every Boolean equation that we had before has a nice-ish representation as a polynomial. The problem is now, how did we basically solve that now? So we basically exchange the exponential blow-up in one part of the formula for an exponential blow-up in the other part of the formula, but now we still have to minimize the polynomial. And this is basically where our new approach starts. We found that minimizing this polynomial by computing a Grübner basis usually yields a smaller representation. And so by converting our polynomial to a Grübner basis, which is computationally very feasible for the size of inputs that we are treating, we basically get a small representation. This is not always the case, but in our experiments it heuristically proved very, very useful. And this is then a small representation that we can work on, that we can basically unfold again into a formula and further minimize on. And how does that look like? Well, the full minimization basically starts with a minimal DNF that we built from our measurements, which is basically the truth table just concatenated together into one DNF formula. This DNF formula then gets quickly minimized with espresso, which yields a slightly better formula that still suffers from these explosion problems that we talked about earlier. Then we convert that into a polynomial, which then indeed gets converted into a Gröbner basis that represents the equivalent polynomial, and that then gets unfolded into a minimal formula again. And this minimizes arbitrary Boolean logic, but is efficient for our use case. So this is not an approach that generally is efficient, but one that works very, very well for what we are doing. And this is functions that have a very low depth and contain many XORs. And this makes minimizing these functions practical feasible. So whereas before it took multiple months, this can be now done in a single day. And we basically experimentally evaluated that by measuring 10 functions, and we found 3 new nonlinear functions, and we also found for 3 functions that were basically inferred in the previous literature manually, we found minimal forms for them. And this also led to basically precise attacks that we could build out of that. So I said before that an attacker that knows about these hardware configurations basically and these microarchitecture hash functions can mount more efficient attacks. And so we showed that prime and probe attacks can be performed using these reverse engineered functions, and they had very, very good accuracy out of the box with between 99 and 97% of correct key recovery if you use a vulnerable AEST table implementation. So we showed that it works with AEST tables, but it would work with any other side channel vulnerable cryptographic implementation and yield very, very nice and precise results. And the brute force effort for an attacker on an AES implementation would be under 1 second, which is very, very practical. So what should you take away from this presentation? Well, we presented an automated approach towards reverse engineering hardware and in general microarchitecture hash functions, which are very present in today's CPUs and are going to become more and more complicated as the CPU becomes more heterogeneous. We also showed a general logic minimization step for a specific function class, namely ones that contain a lot of XORs and are very flat. And in our future work, we hope to extend this work to both reverse more hardware and also look for new use cases for this function minimization approach.